Hey guys, this is Professor Janacek. I want to go over some examples where we work with vectors. To begin with, suppose we have, in still air, we have a parachute with a payload that falls vertically at a terminal speed of 4 meters per second. We want to find the direction and magnitude of its terminal velocity relative to the ground if it falls in a steady wind blowing horizontally from west to east at 10 meters per second. So, to begin with, let's take a look at what this situation looks like. We've got a parachute that's falling vertically at 4 meters per second. So that's going to be negative 4 meters per second since it is falling in the negative direction. And we also have a wind that's blowing from west to east horizontally, and that's at 10 meters per second. Basically, we want to find the result of that, so our resultant vector when we add those two. That's what we're looking for. We'll call that vector v. So let's think about this. We've got vector v can basically be described as the sum of the two vectors that we've got. So that's the negative 4 vector, which we can write as 0, negative 4, and the one going from west to east, 10 meters per second, that one is 10, 0. And very simply, if you add these, we get 10, negative 4. Now we want to find the magnitude and direction of this. So let's start with the magnitude. Easy enough. The formula for magnitude, we're going to take the square root of the sum of the squares of the components. So it's going to be the square root of 10 squared plus negative 4 squared, which gives us the square root of 116, I believe, which we can simplify just a bit. That simplifies to 2 square root of 29. All right, so there's our magnitude. What about the direction? Remember, the direction is the inverse tangent of the y-coordinate over the x-coordinate, so negative 4 over 10. Of course, we can reduce that, and we get the inverse tangent of negative 2/5. Now, it is possible to get a decimal approximation of this, but I'll stop there for that one. Okay, there we go. On to the next example. A boat is towed with a force of 150 pounds with a rope that makes an angle of 30 degrees to the horizontal. We want to find the horizontal and vertical component of the force. So here we're going in the reverse direction. You'll notice in the first example, we had the horizontal and vertical components. And we found the magnitude and direction. Now what we have is magnitude and direction, and we want to find the horizontal and vertical components. So looking at this situation, just so you know what's going on, our vector is 30 degrees from the horizontal, and it's a force of 150 pounds. So it looks something like that. So what I want to do is I'm going to go ahead and draw my right triangle in here. And I basically want to figure out what are the x and y components of that. Recall that the cosine of our angle is x over the hypotenuse. I'll call that hypotenuse r. And the sine of our angle is y over the hypotenuse. Again, so y over r. Okay, so that means the cosine of 30 degrees is x over 150. This tells us that x is equal to 150 times the cosine of 30 degrees. But we know the cosine of 30 degrees. Hopefully that's the square root of 3 over 2. And so we can reduce this and we get 75 square root of 3. That's the x value. Now for the y value, we know that the sine of 30 degrees is y over 150, which tells us that y is 150 times the sine of 30 degrees. We also know the sine of 30 degrees. Sine of 30 degrees is 1/2. So we can reduce this one as well, and we end up with y is 75. Therefore, the horizontal component of our force is 75 square root of 3. And the vertical component is 75. Okay, on to example 3. Let us geometrically describe the set of points x squared plus y squared plus z squared minus 8x plus 14y minus 18z is greater than or equal to 65. Well, what we're going to have to do to begin with is complete the square on these. Let's go ahead and first collect the x's, x squared minus 8x. Collect the y's, y squared plus 14y. And collect the z's, z squared minus 18z. Still greater than or equal to 65. If we complete the square on each one of these groups, we have x squared. Oh, by the way, there's supposed to be an x in here. X squared minus 8x plus 16. Completing the square in the y group, we have y squared plus 14y plus 49. And completing the square on the z's, we've got z squared minus 18z plus 81. But of course, to balance things out, we need to add all those values. We're going to add the 16, the 49, and the 81 all on the right-hand side. If we add those up real quickly, let's see, we get 121. No, I wrote that down wrong. 211. That's better. Okay. Now we actually factor each one of these groups. If we factor x squared minus 8x plus 16, that gives us x minus 4 quantity squared. Factor y squared plus 14y plus 49, we get y plus 7 squared. And factor z squared minus 18z plus 81 gives us z minus 9 squared. And that's all greater than or equal to 211. Which, by the way, I see where this is going already. We've got all these squares. This is starting to kind of look like the equation of a sphere. And I know that whenever we deal with these, we usually want to write our the stuff on the right-hand side as the radius, so it's the square root of something. So I can write this as the square root of 211 squared. Now everything is exactly in the form that we want it to be. Notice this is an equation of a sphere. Its center is 4, -7, 9. Watch it, that 7 is negative. And its radius is the square root of 211. So, how do we describe this? Now, I do want to point out that this is greater than or equal to. So, equation of a sphere usually just has an equal to. What does it mean if it's greater than or equal to? Well, that means we are looking at, all points outside the sphere. That's centered at 4, -7, 9, with the radius square root of 211. And notice, because it has that equal to, so that's greater than gives us this, but we also have the equal to underneath that. So that means this is including the sphere itself. So everything outside of the sphere, including that edge of the sphere. And there we go. On to example 4. We have two vectors. U is -2, 3, 0, and V is 1, 2, 1. Let's determine the magnitude of 4U minus 3V. I'll do this in pieces. Let's first write out what is 4U. Well, 4U is simply 4 times each component of our vector. So we get -8, 12, 0. And then we also want to find -3V. Notice I'm going to go ahead and keep that negative with the 3. It's much easier than having to distribute it later. So -3 times V, -3 times each of the components of V gives us -3, -6, -3. Now if we put those together, 4U minus 3V, it's really just a matter of adding those two vectors we just wrote down. So putting those together, we get -11, 6, -3. And finally, to take the magnitude of this vector, remember that's the square root of the square of each component, or the square root of the sum of the square of each component. So square each of those, add them all up, take the square root, we end up with what is that? $166. And I think that might be prime. Well, I don't think we can take the square root of that. And so we'll stop there. Enjoy.